recording now. All right, so this will be the important part. All that other stuff was fluff in the beginning. All right, so if you're at the table, you'll notice that this table is not, and we will get to this table, the other table, but this table is about a voltage correction factor, right? Which is not something that you've looked at so far. But DC is affected by cold temperature, right? The old throw the battery in the freezer and you get more life out of the battery. That is not fake. That is real. All right. Now it's fake that you get, the battery charges up, but the voltage does come up a little bit. So when you remove the battery from the freezer, you can put it into a flashlight and, oh, the battery's working again. It'll die because you just put it in the freezer. But that's the case with all DC voltage. It is affected by cold temperature. So the first thing of note to highlight or write down or make a note of, because it is going to come up as a question, is when do we have to make this voltage correction factor? And that's when the temperature that the conductors are, the conductors and the equipment, anything outside, which is where our solar panels are, as soon as that drops below 25 Celsius or 77 Fahrenheit, which it is less than 77 Fahrenheit outside right now, I think, maybe not. Ooh, we're right at 77 here in Chattanooga. So the solar system would still be harmonious. But this week we're going to get 52, next week rather, 52. So now it's affected. So there's a table. Going back over to the code book. The table is very simple. It's not complicated. The other table that we'll look at is a little bit more complicated, but this one's quite easy. You just have to pay attention to whether or not you're being asked about an ambient temperature in Celsius or an ambient temperature in Fahrenheit. There are overlapping numbers. As always, you can see all of the negative numbers down here. There are the same overlapping negative numbers on the Celsius side as well, but different correction factors for those. So as long as you don't get lost there, this could not be, this is not going to get that much more difficult. So here's how it works out. All right, and we can go into yesterday just to take one step back. I have 1, 2, 3, 4, however many, let's say 4 solar panels outside. Connecting them all in series with each other. And let's say each one of these is 12 volts DC, meaning that now my total voltage is 12 times 4. So I have 48 volts DC being produced at the end of this. One of the things that we didn't really get into yesterday, because it really doesn't matter too much, but it is part of this correction factor now, which is the the inverter. I was going to say converter, but the inverter, the one that is going to receive this DC voltage and then convert it to AC, has a maximum voltage capacity. All right, they all do. All right, they all have a maximum voltage capacity. See if I can pull one up and go into the specs. Doesn't really matter, but just to give us some numbers to look at. I don't want to get too far down the rabbit hole of looking for specifics. Yesterday's stuff was good, but now today, sometimes I pull this up and it doesn't give me the same companies that I had yesterday. So then I'm trying to find the same thing I showed you guys or the PM class. It just pulled up, but and let's see if I can go over to my inverter. Okay, here's the inverter. So this inverter, as you can see, has a maximum voltage input, max PV voltage input of 500 volts. All right, so there is a maximum voltage that this can handle. And coming back over here, when the temperature changes, it affects this voltage. All right, so all we have to do with this code section, and that's why I said no big deal to pull that up, nothing else really I just wanted to point out, other than the fact that they have a maximum voltage input on the inverter systems. Same thing for the batteries. Same thing for the, I mean, that's a high voltage. I thought it was somewhere in the 50s, but it is somewhere, yeah, 500 DC for that one. Okay. So using the table now, right? The next thing that the factor is going to come in is what's the temperature that these solar panels are in. So let's say it's cold, right? Let's say it's dealing with whatever, 6 degrees Fahrenheit outside. So now we're going to come back over to the table, and that's all we have to do now. We have to find 6 degrees Fahrenheit, which sits, I'll try to highlight it, but not the best highlighting for this PDF, but it's sitting there between 13 and 5 because we are on the Fahrenheit side. And then our correction factor is 1.16. What that is telling us is that 48 volts is going to go up by 116%. You're going to get more voltage out of this system by 116%. So it looks like that. 48 volts multiplied by 116, which I'll do real quick, changes our voltage to 55.68 volts DC. So if I had an inverter that had a maximum voltage input of 50, then this changes how I can organize these solar panels and connect to this particular one. All right, and some of them do have these lower ones. I'm trying to find these lower ones so that I can point it out for these inverters, because that inverter that I showed you was for a home system, and that ended up being very big. But there are much smaller. That was a 20,000, so that's why it has 500 volt capacity. But the smaller they are, then the least they can, the less voltage that they can handle. All right, so smaller systems with standard inverters that are just going to be connecting to, let's say, one or a few solar panels, then they do have a much less voltage input capacity. And so you just have to monitor that, all right? So for the questions, we don't have to get that far as to, you're not going to go buy an inverter or pick an inverter. The questions will, whoops, I meant to erase, show exactly that. All right, what is the correction factor for 48 volts DC with an ambient temperature of 6 degrees Fahrenheit? We start with 48 volts. That's the voltage that we start with. We multiply that by 1.16, and now we have, what was that, 55?
55.68.
Thank you, sir. 0.68 voltage DC adjusted. So we start with 48, we adjust it up to 55.68. Things that can change in this question that are going to look different on the final exam, I'll put a different voltage, and I'll put a different temperature, say -4 degrees Celsius now. All right, if it's -4 degrees Celsius, then same thing. We come back over to the table. We are on the Celsius side now, so we're over here. We find, yep, 1.12, and now we adjust the 12 by 1.12. And whatever that is, 13 and some change?
Yeah.
13.44. All right, as long as you know how to do that, you won't get stuck with any of these questions as far as voltage correction factor. But I do want to point it out because, again, DC does change. And it is something that you'll need to understand, that the colder the temperature, the more voltage you get out of DC. Sometimes this is good because of voltage drop, but in this particular case, it's not so good if my piece of equipment can't handle that max voltage. And then you would just have to change the combination. Like I said, if you have 4 of them and 4 of them are at 48 and then the cold temperature takes it into the 55, and your inverter is maxed out at 50, then you'd have to either drop one solar panel or maybe shift the connections to two in series, parallel, like start playing around with the parallel and the series connections to be able to do it. As always, whatever you do on one row, you have to match on the other row. The voltage and the amperage have to match if you're going to be connecting them back together. It's like I said, it gets all messed up when well, first of all, if there was different voltages, it's going to get messed up because you are going to short that out. Technically, it's not a short circuit, it's just two different voltages coming together, but I guess at the end of the day, it can be considered a short in that resistance goes to zero. All right, so a few things again. Know the article the voltage correction factor comes from. Know the temperature that we have to start changing the voltage at, and then, like I said, keep in mind Celsius versus Fahrenheit from there. Not too difficult. All right, now let's get to the harder table of these, which is going to be on page 608 is where we'll start. One table, the other table is on page 609, and it's going to be Article 690.31, and the table is Table A, subsection 3, and then not half, it's just there's two of them. 690.31A31, 690.31A32. So I put it like that. Probably looks like half, but not too critical to. But this is the first table here, right on page 608. So as you can see, we have some things that we might be familiar with already. AWG, American Wire Gauge. We have the gauge system that we understand. All right, all the same ones up to 4-aught. All right, 18, 16, 14, 12, all the same numbers all the way down. So the gauges are the same. What changes is the temperature of the insulation for these conductors. That's why I said you can't use the old conductors because they have a different temperature or insulation rating. Temperature insulation rating. So those max out at 90. This starts, the smaller one here is 105 degrees Celsius temperature rating on that insulation, PVC or just polyvinyl chloride, not to be confused with the conduit. CPE, which I don't know what these stand for, XLPE. There's another XLPE, so anytime I'm using this one, I will be telling you which one I'm talking about. And then EPDM. All right, and just like with the 60, 75, and 90 degree column, the amperage changes as the insulation temperature rating changes. You get more amperage being able to being held by the conductor when you choose a higher temperature rating. It's the same thing as if you choose a number 12 from the 60 degree column versus a number 12 from the 90 degree column. The 90 degree column conductor will be able to hold more amperage. So all of those same factors show up here. Say, for example, a number 8. All right, we have the number 8 here. Let's say look at the number 8's amperage in the first column, 105 degrees Celsius, 64 amps. Look at it on the 125 degrees Celsius column, it goes up by 5, meaning it can hold 5 more amps. All right, bigger jump as we get to that 4-aught. The 4-aught can hold 24 more amps. So there is a difference between these two. So that's the first thing, is just know how to find the ampacity. That's what this is called, the ampacity of the conductors, right? Remember that word ampacity? It's up here now. Ampacities of insulated conductors rated up to 2000 volts, 105 Celsius through 125 Celsius. We're in America, but we never even concern ourselves with the Fahrenheit for the other conductors either. Same rule, no more than 3 current carrying conductors in a raceway, cable, or earth. And the temperature correction factor begins once we now in this case, increase higher than 30 Celsius, 86 Fahrenheit, which
Is that like 257 degrees Fahrenheit is ridiculously hot? Is that the temperature inside the cable?
no, that is the temperature that the insulation of that cable can hold.
Can
So
hold.
yes, yeah, there is no conditions outside that will ever destroy this cable.
Yeah. So I mean, why would there be such a difference between the two then? Like, when would we use those?
You're saying
Like like 257 degrees is very high. I don't know what example you would use to,
so the trying to understand.
like
So these are the wires that we have for solar systems. The so you're saying when will these wires ever face this temperature?
yeah,
Never,
basically,
never.
exactly.
But that's the point. The wires should never face that temperature. But say for example, they're on the rooftop. The sun's out. It's middle of the day. It's 100 and something degrees, 105, 110. They're near metal. There could be all these other factors why the insulation might be dealing with a little bit more temperature. Say like 120, 125. That's good. What we don't want is for that to be happening every day, and then slowly we start to eat away at the insulation.
I see.
With the other one, it's 90 degrees Celsius, which I don't know what that is in Fahrenheit. I don't remember the other ones, but it shouldn't be too far away. Let's see here.
So it's kind of like overkill, basically.
Basically. Let's see. Let's ask ChatGPT. So 194 degrees Fahrenheit. Your regular wires, the THHN, the one that we use to run to these outlets, the insulation is rated for up to 194 degrees Fahrenheit.
Mm.
So when are those wires ever going to face that? Never, but that's the point. The insulation, remember, it's also dealing with amperage, so there's amperage factors internally. Conduit, it starts to get hot in the conduit. So all of these things play a role, and so 190 degrees Fahrenheit for THHN, not allowed to use it for solar because solar feels not enough protection.
Nice.
We got to bring that up even more. But don't focus so much on the Fahrenheit because, again, we will always reference these conductors by their Celsius. Same thing for, you did the 90 degree column, not the 194 Fahrenheit degree column. We still call it the 75, 60, 90. So we use the Celsius numbers. So the first thing to be able to do is just to find the ampacity based off of the insulation. So for example, the question could be as simple as that. What is the ampacity of a number 4 with EPDM insulation? That's just the question. What's the ampacity of this wire? So you come to the table, you find that insulation, happens to be sitting in the 125 degree column this time. Scroll all the way down till you'll find 118 amps, or ampacity. Ampacity just means the amperage the wire can hold. That's the word for that. All right, the amperage the wire can hold. Remember, the wire doesn't have this amperage. The wire is connected to a system, panel, whatever, that is going to deal with up to, and the wires are good, up to 118 amps. All right, so any wire, any insulation type, find the ampacity. That is step 1. All right, now let's get into the more confusing side, just because the way they designed this. The other table, which is just on the next page. I scroll down, you guys can, it might be on right next to it. I'm not sure if these two pages are side by side. It'd be nice if they are.
They are, yeah.
Perfect. Now, this is the table with the correction factors. The correction factors sit in the middle. All right, starts with 0.97 for both first ones, and then it starts to work its way down and work its way down. And the correction factor here starts to get smaller because as the temperature gets hotter, and that's what's happening as we're going from 86 Fahrenheit, for example, to 248 Fahrenheit, the temperatures are obviously getting hotter. So as the temperature gets hotter, the less amperage the wire can hold. All right, the first number is actually 1, meaning the wire can hold at 86 degrees Fahrenheit or 30 degrees Celsius on the other side here. The wire can hold 100% of the amperage. All right, so meaning this number 4 can hold 118. But if this number 4 wire is in, let's say for example, 106 degrees Fahrenheit, now it cannot hold 118 anymore. So you are going to find the correction factor, and this is where it gets confusing, based off of the temperature of the insulation. In this case, our insulation is EPDM, and it sits in the 125 degree column. So when we come over here to this table, we have to pick, since we were dealing with 106 degrees Fahrenheit, our correction factor is going to be 0.92. So we take this 118, take away, that's what 0.92 is telling me, that we're going to take 8% out of this 118. This is how we do it mathematically. But that's what that means. It means that wire is going to hold 8% less amperage. 0.92. Not a big loss, but it's still a loss. Oops. Still a loss nonetheless. Almost went up. 0.56. So 109. Now, this hasn't been confusing yet, but I'm going to make it confusing now. Let's say the temperature that we were dealing with, right? So far so good, right? You've already done this. You did this when you were dealing with Article 3.10.16 and changing the ampacity of the conductor based off of temperature as well. Now, let's say the wire is sitting in, right? This wire right here is sitting in, let me pick a number, 73. Let's put the number over here, right in the middle. 73 degrees Celsius. Okay. Now, again, it's not confusing, but it is a little bit confusing just because your eyes are going to want to do something, and I'll explain. Let's find the 73 degrees Celsius, right? Sits over here on the Celsius side between 71 and 75. Instinctively, you are going to pick 0.63 because it's right next to it. But we have a problem with 0.63, and that is that the wire that we're looking at sits in the 125 degree column. So the correction factor is not 0.63, it is 0.73 because it sits in the 125 degree column. Even though, again, we were over here on the Celsius side, but your eyes are going to want to do this, and it happens to me even explaining this sometimes, where I'll just go right to 0.63 because I found the temperature on the left side, and so my eyes did not jump over to the right one. It is all based off of the temperature of the insulation type. That's where the correction factor must come from. So, for example, this one now becomes 118 times 0.73. And again, 0.73 means that I'm going to be taking away, what, 27% out of this wire? That's a lot now. 118 times 0.73. We dropped. We lost a lot. We lost almost 30% of the wire's amperage capacity. We dropped all the way down to 86 amps. So the hotter it gets, the less amperage the wire can hold. One little added bonus to trickiness is that column that you have to make sure you're on based off of the temperature of the wire. So I'm going to give you guys one to do on your own. Unless somebody was writing all of that, I can come right back to it. So let's say we have a number 2. Insulation type CPE. With a temperature of 160 degrees Fahrenheit. So I'm going to pause here and let you guys try to solve this. I may not have gone over this enough right now for you to get there, but at the very least, you should be able to find the ampacity of the conductor, and then from there, look at the temperature that I gave you, and go find the correction factor, and hopefully from there you're able to do some math. I'll start doing it also. Just so when I ask, all right. Has anybody got that final answer?
I think so.
All right, let's put some numbers here on the board before we jump into that section. So a number 2
Is it 90.9? Oh, no.
90.9, very good. Nice, well done. The number 2 has 143 amps is where we start at. All right, just to come over here, make sure, you know, the other thing that you can forget, number 2 is not too hot. So number 2, CPE was the insulation type. Right, so 105 degree column, 143 amps is where we start at.
Yeah.
Now the temperature I gave us was 160 Fahrenheit over here. However, don't pick 0.73 because the wire is a 105 degrees Celsius. CPE is 105, so very good picking the 0.63. And then yes, if you multiply 0.63, this is where you get 90.09 amps. All right, so to run through the names again, this is the ampacity of the conductor, and this is the adjusted ampacity, based off, again, the temperature that the conductor is sitting in. All right, so ampacity, adjusted ampacity. All right, good so far. This will be a short class, just given where we're at right now. And I only have one last thing to show you, and then we'll wrap up. Also, I don't want to overwhelm anymore for the final. We have one last day, so tomorrow we'll be reviewing. There is one last thing that I am going to point out after we get through this math, but it's only important because of the fact that this is DC. I do want to show one last thing, but it isn't mathematical and it's just out of the code section. All right, so we got this. We'll do some more practice tomorrow. Now, here's the other way this question gets asked, which is, what if I still need to cover 143 amps? Right? I wanted the number 2 CPE because it can handle 143 amps. But reality is this wire is going to be sitting in 160 degrees Fahrenheit, and this could be, again, outside rooftop, in the conduit. It could be factored in because the wires or the equipment have gone into an area where there's a boiler, industrial hot conditions that can all factor in. So because of that, now this wire can't hold 143 anymore. So what do? I still want a wire that can hold 143. So now I got to go searching for a larger conductor that when I take away the, technically not 0.63 is not what we take away. The part of this that gets taken away is the, 37 amps on the other direction. But when in other words, when I run the wire through this 0.63 correction factor, that adjusted ampacity number is bigger than 143. All right, so that's the idea. So let's take a fresh page and work this out. The way the question will look or be asked is, for example, what size wire, I could even write it out, conductor wire, whatever, do we need for 100 amps, let's say, actually, we'll add something to this. What size, and here's where we'll put the insulation type. What size, let's go with PVC. Remember, this is the insulation, not the conduit, because you can go, oh no, we're gonna go look for a conduit. No, insulation type. What size PVC insulation type is needed for, now we'll do 100 amps with an ambient temperature of, I meant to underline here as well, of, and then whatever temperature I give you. Let's go with, let's go this time with, where are we at? Okay. Let's make it hot. Let's make it hot. Let's go with 188 degrees Fahrenheit. Let's start there. So this is how we can do it. All right, we can do this in one of two ways. There are two ways that this calculation can get done. When I first started to do this, I was taught the way I actually think is a little bit more difficult. All right, so keeping with multiplication, right? If I got to cover 100 amps and I got 188 degrees Fahrenheit, then that's going to be a big temperature change. So I can come over here to this table. I can start at this table. All right, I can look for PVC, got it. I can look for a PVC wire that can hold a little bit more than 100, but now how much more than 100 I don't really know. I'm technically gonna be guessing here. So let's go with 104, the number 4 it can't be is 109. I'm trying to cover 100 amps. That 9 is not gonna, that's gonna get blown out of the water once I go through this correction factor. So let's go to the next one. Let's go to the number 3. And that number 3 can hold 129 amps. So that's where I'll kind of start my guessing game. All right, I'll start with, it might not be the end wire that I end up with, but I'll start here. 129 amps multiplied by the correction factor for 188 degrees Fahrenheit. Now, again, you got to make sure we're in 188 degrees Fahrenheit, which is over here between 186 and 194. But our correction factor, because it's a PVC conductor, is 0.45. Very good. Now, let's run this 0.45, and already, we could already take a educated guess here and go, you know what? 0.45 means I'm losing 55% of the wire's amperage. If I take 55% of 129, you're going to get way less than 100. But we'll run the math just so you can see this. Times 0.43 equals. Okay, 55 amps. Well, wow, that is way too low. Right? I gotta cover 100, so 55, no way.
No.
So here's where we go into guessing again.
It's 58.07.
Sit 50. Is it?
50. Yeah, 129 multiplied by 0.45 is 58.
Oh, sorry, I did 0.43. Yeah. Sorry. So what is the number? 58?
8.05.
All right, thank you. 58. I don't know why I did 43. 0.05. Okay. Still not enough. So we go and back to the drawing board, right? Back to the wire table and go, all right, well, that was way too low. Now that I know that I'm going to lose 55% of the wire, let me go into some higher numbers, right? Let's go with the number 1, maybe a 1-odd. Let's go with the 1-odd.
Yeah,
193. So we start with 193 now. And we multiply that by 0.45. And does anyone have that number?
86.85.
86?
0.85, yeah.
0.85. Still not enough. And I've already taken 2 guesses, but now I'm confident that it's the next size higher. Because I'm close enough to 100, right? I'm 12, technically that's 7, so 13 away.
15.
Yeah, so it's almost 100% that it's the 2-odd, 229. You could always run the math if you want. 229 times 0.5, 4.5. If I was taking a journeyman exam and it all depended on numbers, at the end I don't want to mess anything up, then I would just to assure myself, and this is 103.5. And so now we get there, 103.05, yeah, 05, not 5. So now that's good. It can cover 100 amps. The wire that we want is a 2-odd. This is the hard way. All right, and this is the way it was taught to me, but this is the hard way. Because of this, because we started at number 3, then we said maybe it's a 1-odd, and it wasn't a 1-odd, then we had to go 2-odd, and then we even decided, let me double check because I don't want to get this answer wrong. So we double check, and it is in fact the 2-odd. There's an easier way to get here. All right, and it's not starting with the wire. Let's erase this. The easier way to get this is step 1, and I could even write it as a step version. Find the correction factor. Start with the correction factor first. So 188 degrees Fahrenheit, you make sure that you have the right insulation type. We already found it was 0.45, but you go to the right side of the table, or the correct column on the table, and you start with that, 0.45. And now you're going to divide by the amperage you seek to cover. And now you divide 100 divided by 0.45, and it's going to come up with the number 22222 at infinity. I think it might end somewhere, but 222.22 amps. Now, this is all you have to remember is next size higher. This never happens, but I always say it, unless you land on a wire number. All right? It's never going to happen because we have decimals. But it could be that you land on the right number if, like, say the decimal is 0.5 and you increase and you get to a whole number. So it's the number or higher. So 22.22 or higher. Meaning that when I come back over to this table now with the wires, there is no 222. So the next size higher is 229 or the 2-odd. Right? Or the 2-odd. Meaning that I got to the answer immediately. This is the easier way to do it as long as you remember next size higher. And now it doesn't matter, because here's when this really becomes a problem. And this is why I chose 188 Fahrenheit. It's when it's that different of a temperature. You know, if, for example, I would have said the temperature here is 125 degrees Fahrenheit, then the correction factor is not that much. Right? We can come over to the correction factor here for 125 and 0.82. And now I could have guessed probably that number 3. Right? Going back up here, probably the number 3 at 129. Right? 129 times 0.82. All right, I'm losing, not a little bit, that's enough, but I'll show you what I mean. 0.82 equals 105.78. So perfect. So when the temperature is not that much different, like not that high, it stays relatively low, and your correction factors are in the 80s and 90s, then it doesn't matter. You can multiply. But why do all that when you can just apply the divide to any temperature? Always just divide. All right, let's try another one. Let me erase that. Let's erase the amperage. Let's erase this, but we'll keep the steps. All right, let's say this is now a EPDM insulation type. Let's say the amperage that we want to cover here is going to be 80 amps. And let's say the temperature factor is, let me pick a number that is relatively good. Let's go with 72 degrees Celsius. All right. And I'll pause here, let you guys answer this one again. If you use the steps, for me, it's the way easier version of how to do it. Ooh, nice. Good work, by the way. Everybody's pretty much, except for 2 and yeah, pretty much nailed it for the course evaluation. Thank you, guys. We're at high numbers. Doesn't tell me percentage, but I guess I can run the math. All right, so for this one, 72 degrees Celsius, again, find that correction factor first and foremost, and it should be 0.73, right?
0.73, yep.
Perfect. Divide by desired amperage of 80. And now you do 80 divided by 0.73. And you get 109.58. Important to always look at those decimals because this becomes 110. This is what I meant. If there happens to be a wire that's 110 in the EPDM column, then this is our wire. If not, next size higher. There isn't one, so by default it has to be the
118, so 4.
Number 4, excellent. EPDM. Alright, this for me, I forget, I got taught this after the fact, but I remember when, because I went through 2 schools, sort of. I went through the union apprenticeship, but the union apprenticeship is a little bit different than it's the same course that you guys do. This was in the late 90s, so obviously there was different material. You know, we didn't have PLC classes and motor control. Solar wasn't obviously a conversation yet. But we had a lot of the other overlapping things, like 31016 has always been 31016, and wire sizing and conductor sizing. So I did this when I was in the journeyman, when I was in the union apprenticeship, they taught me the multiply. Because whoever was teaching, that's the one they learned. But then, because years after, not many, but like, you can get your journeyman license in Dade County, which is where I got my first journeyman license, after 3 years of working in the field. Like, not at the 3 year, at like the start of your 4th year. So after you've completed all of the 3 years of working for an electrical contractor, you can sit for a journeyman exam. But I had not done a lot of the calculations, you know, for 2 years. So I went to a journeyman prep class that prepares you for your journeyman exam, and that teacher was the one that taught me the divide. Why? There's a point. Because that teacher was focused on speed. They were preparing me for a journeyman exam that was timed. The other teacher didn't have a time factor to deal with. So multiply, if you don't have a time factor, yeah, guess the wire, multiply it, didn't hit the number, multiply by the next wire, didn't hit the number, multiply again, find the number. All right, but that could take you 2 minutes. And on a journeyman exam that you have 20 questions, 30 minutes, you have about a minute and some change for each question. I don't have 2 minutes. So they ask me 4 questions like these, and I take 2 minutes on each question. Right? Now we have 8 minutes just on these 4 questions. Yeah. So that's why this person was like, no, do the divide. You cut your time by a lot. And so they were focused on micro minutes, you know. If I can get you to answer a question that took you 1 minute, if I can get you to answer it in 30 seconds, we just gained 30 seconds. That comes back to us for questions that we are going to need a little bit more time on. So keep that in mind, you know, just keep that in mind. For my exams, we have plenty of window of time frames. If you wanted to do the multiply, fine. But I would always suggest and encourage you to practice the things that are a little bit faster. Just to get into the habit of that, because there will come a point where you're going to have an exam that's timed to the effect of you needing to